Natural disasters. Climate change. Overcrowding. Big problems demand even bigger solutions. It's a new era for engineering. We can build our way out of anything. Under the Bering Strait, to feed a global appetite for goods and energy, the longest underwater tunnel in the world. This is mega engineering.
Welcome to the Bering Strait Tunnel. You are now leaving the United States of America and entering the Russian Federation. Have your passport ready for inspection.
Just inside the Arctic Circle lies the Bering Strait, a narrow seaway that separates Alaska and Russia. It doesn't seem like there's much out here, but some see a gold mine. Here, Russia and America almost touch, separated by 55 miles of icy ocean. To the east, the U.S. economy, consuming 25% of the world's energy. To the west, in Russian Siberia, a trove of natural resources. Oil, diamonds, and some of the largest natural gas reserves in the world. South of that, Chinese ports crammed with goods destined for the U.S. market. Today, nearly 75% of all goods traveling between North America and Asia move by ship. But what if we could replace these with this? What if Chinese goods could reach the U.S. in days instead of weeks? By traveling through an underwater tunnel between Asia and North America, Russia could supply the Americas with all the natural gas they could ever want. A railroad and a pipeline, stretching all the way from Shanghai in Siberia to Los Angeles. Because of the Earth's curvature, a train route from China up through Russia and over to the U.S. can actually be shorter than shipping from Asia across to California. The tunnel would cost up to $70 billion, but it could save trillions. It would be an engineering feat unprecedented in scale and difficulty. To construct it, builders would have to solve extraordinary problems. At over 60 miles, it would be more than twice the length of any existing tunnel. It would have to stand up to brutal Arctic conditions. Building materials would have to withstand relentless freezing and thawing. Construction crews would have to work at the bottom of the Arctic Ocean. And on the surface, endure temperatures of 40 degrees below zero.
You can go into hypothermic shock really fast, and you won't realize it at first when it happens.
Engineers would need to design a fire-safe tunnel. Capable of withstanding frequent tremors and an earthquake up to 7.9 on the Richter scale. Impossible? Maybe not. Workers are already tackling similar problems half a world away. In Istanbul, Turkey, builders are using new techniques to construct one of the world's deepest tunnels. Here, crews are building an underwater train line beneath the Bosporus Strait. Istanbul is a divided city, with one part in Europe and the other in Asia. Like the Bering Strait structure, this tunnel will join two continents and span a vast sea. With a population of 11 million, this ancient city is one of the most congested in the world.
In Istanbul, we are currently having a very serious traffic problem. even though we have 2 bridges for motor vehicles. Once the project is completed, both continents will be connected by a suburban train and an intercity freight and public transportation system.
Bridges are expensive and interfere with shipping traffic. So to add capacity, planners have opted for a tunnel instead of another bridge. Their plan calls for an 8.5-mile-long underwater railroad line to carry cargo, cars, and trucks 150 feet beneath the sea. To build it, they are using an innovative design called a submerged tunnel. Surprisingly, the entire structure is actually built on land. Then pieces of the tunnel are floated out and assembled underwater. It's a technique that might work in the Arctic, with a few modifications. In Istanbul, workers first built a massive dry dock, where they constructed 11 442-foot-long boxes called elements. Each element is wide enough for 2 trains to run side by side. The crews then floated each box out into the strait, positioned it precisely above the seabed, and sunk the element.
You hang the boxes from several points, and when you take water into the elements, it will be heavier than the water, and gradually you can lower the elements to the seabed.
Once the segments were connected underwater, the tunnel pieces were buried in sand to protect them. Now, in the last stages of construction, the elements are still connected to the surface through access shafts in the middle of the strait, one of the busiest commercial waterways in the world.
There are huge vessels passing through the Istanbul Bosphorus, and it is very risky for us during the construction.
If a ship were to go off course, even a little, it could crash right through the work site, flooding the tunnel. But that's not the only worry. As near the Bering Strait, this is earthquake country. A quake could be devastating to the workers 150 feet below. In an emergency, their only hope is an underwater chamber stocked with vital supplies, what they call the panic room.
We are going down 150 feet to reach the 11 elements below.
Hasan Gökdere is the site foreman.
There are about 30 people down at the elements, and we're going down to check on them.
Hasan is the only person authorized to escort visitors down to see the panic room and the inside of the tunnel.
We are currently 150 feet below the Bosphorus Strait. In case of an emergency, like a breach in the tubes or shaft, we all come to one of these panic rooms. This is the panic room. This is the water supply. This is the food. And this is the communications link to the land site.
Şaftın kırılması durumunda kullandığımız odamız. Bu gördüğünüz hortumlar ve vanalar da yukarıdan bizim.
These pipes and valves are what we use to supply air to the workers. Here we can supply air up to a maximum of 40 people for up to 10 days.
Yaşayabilecekleri havayı sağlıyoruz.
If the tunnel were to break open, the rupture would likely happen at one of these joints. This is where box numbers 6 and 7 meet. Up on land, each element was walled shut. Down here, crews first weld the boxes together at these joints and then carve out the inner walls. It's the most dangerous step in the process. Once the walls are removed, the joined elements form one long rectangular tube. This team is now cutting down the protective walls between sections 7 and 8. To break through each steel wall, the crew has to remove 40 tons of metal. 3 weeks of hot, back-breaking work. Now the team is just months from completing the tunnel that they began to build 6 long years ago. The submerged tunnel is one of the fastest and least expensive methods of underwater construction. And in Istanbul, it's well suited to local conditions. But could it work in the Bering Strait? The most obvious difference between the two locations is on the surface. The Bering Strait is frozen almost 10 months a year, which could dictate much of the construction process. This way, during the long winters, crews could save the cost of building a dry dock. They could build their segments right on the ice, directly above where they want to sink them. Then in the summer, the segments could quickly be submerged. But it turns out that the most significant obstacle would be below the surface. For a submerged tunnel to work, as in Istanbul, engineers need a smooth sea bottom and soft soil in which to lay the tunnel. But under the Bering Sea, the seabed is sometimes rocky and it's full of uneven hills, so the topography could complicate construction. That means that engineers may have no choice but to turn to a slower, more expensive, and even more dangerous method. They'd have to carve a tunnel below the sea floor. If engineers can't submerge a tunnel below the Bering Strait to link Alaska and Russia, then they'd have to dig a tunnel below the seafloor instead. That would mean carving through more than 60 miles of Arctic rock beneath a frigid ocean, doubling the length of any underwater tunnel. Luckily, recent advances in the design of gigantic tunnel boring machines, or TBMs, could make such a feat possible. TBMs are building-sized machines that can grind their way through almost any kind of rock. The Bering Strait Tunnel would require a machine similar to this one, the Herring Connect Gripper, specially built for the Goddard Tunnel project in the Swiss Alps. With 14,000-foot peaks, the Alps are some of the tallest mountains in Europe. And just south of Zurich, engineers are boring a double railroad tunnel 35 miles long, straight through the mountains. When completed, it will be the longest tunnel in the world. The new route will save the Swiss millions, replacing an old, inefficient system.
The existing line goes over the Alps. Trains cannot be very heavy because they have to go up 2,000 feet and they have to go down 2,000 feet. On this line, the train will be much longer, much heavier, and they will go through the Alps, not over.
Like boring Arctic rock, cutting through this mountain is no easy task. It takes 4 TBMs to get the job done. Adrian Wilbolts has worked in the tunnel for 8 years. He manages one of the 4 crews carving away inside the mountain.
Just here, behind this wall, is the turning wheel. It consists of about 70 discs being pressed against the rock, and the rocks being crushed. And because this wheel has openings like a water wheel, and while turning, the material gets up into the machine and over the conveyor belt all the way out to the construction site.
Behind the cutting wheel, a ganged network of 10 500-horsepower electric motors. Trailing behind the TBM, reaching all the way back to the tunnel entrance, is a network of power, water, and ventilation lines that grows steadily longer as the TBM moves forward. The machine is steered by varying the amount of pressure exerted on these jacks.
First, we have to set it in place by pushing those big grippers to the sides, so the machine is fixed. Then we can add differential pressure on those two steel rods. By adding differential power, we go to the left or right, up and down.
These hydraulic jacks push off of the tunnel lining to keep the cutting wheel pressed against the rock face ahead. With each cycle, the TBM pushes slowly forward until the jacks are fully extended. Then the cutting wheel stops. The jacks contract, and builders construct another layer of tunnel lining, which the jacks use to brace themselves for the next push forward. Workers call the machine the inchworm because of the way that it moves through the ground. Boring a deep tunnel would offer big advantages in the Arctic because it would keep workers underground and out of the cold. And, luckily, the rock beneath the Bering Strait is extremely hard, which actually makes TBM tunneling easier.
You might think hard rock is more difficult than soft rock. It's the contrary. Hard rock usually supports itself, and in soft rock condition, in unstable condition, we have to add lots of supports, and that takes lots of time.
In Switzerland, the Goddard Tunnel team is encountering a mixture of hard and soft rock, which makes tunneling extremely slow. Right now, the TBM has hit a particularly unstable soft spot. The risk is that the tunnel roof near the front of the TBM will give way, potentially burying the machine and its crew. To stabilize the ground, builders add metal netting like a cage. Once they get past this soft spot and get back into hard ground, the crew can pick up the pace once more. At the Bering Strait, engineers believe tunnel boring machines would be the best choice to carve the 30-foot diameter passageways required for trains. But at twice the length of the Goddard Tunnel, it would be far riskier than anything ever attempted before. But no matter what it would take, the benefits of a permanent link between the continents could make it all worthwhile. Massive tunnel boring machines could carve through more than 60 miles of Arctic granite to dig a tunnel beneath the Bering Strait. But that's not the hardest part.
Since its location is very, very remote, the logistics of getting men, materials, and design crews to that location are much more massive than anything that we've done in the United States today.
Engineers face a huge challenge just to get crews and supplies to the Arctic. There are no roads. The sea is frozen most of the year, and aircraft can't carry all the machinery. So the best way to get equipment and crews to a Bering worksite would be by train. On the Alaskan side, the nearest railhead is 750 miles away in Fairbanks. In Russia, it's further. Crews will have to build nearly 2,000 miles of track to connect the Bering Strait by rail. As if that wasn't enough, they'd have to build the railway on unstable ground.
Both sides, we're facing permafrost issues and Arctic conditions, which wreak havoc on anything that we might construct.
And that's not the worst of it. The Russians face a natural obstacle that could deny rail access to the Bering Strait forever. It's the Lena River, an 8-mile-wide killer. The Lena separates the Bering Sea from the rest of civilized Russia. Any food or supplies going north have to cross this frozen blockade.
The Lena River is one of the most significant water systems in Russia. The railroad builders of today are going to have to cross the river Lena to reach the city of Yakutsk. It's an enormous challenge.
Yakutsk is the region's largest town, a former dumping ground for political prisoners. Today, it's the gateway to all points north. To build a railroad up to the Bering Strait, crews would first have to span the river with a railroad bridge. As it is now, there are only 2 ways to cross the Lena: by boat or by air. These small planes and choppers are often grounded by bad weather, and they're unable to carry heavy loads. Without a railroad, cargo going to the Bering Strait would have to be ferried over the Lena, a treacherous journey. Conditions here are so difficult, it takes 2 boats for each ferry crossing. First, an icebreaker carves a path. Then the ferry follows in its wake, carrying semi-trucks, cargo vans, and passengers. Brutal weather conditions mean the ferry can only make 1 round trip per day. In winter, the ice gets so thick, the ferry can't run at all for 4 months. Each crossing is a dangerous endeavor. This ferry would have to bring all supplies for the Bering Strait, unless the Russians can build a railroad bridge to replace it. But that will mean working in sub-zero temperatures, and often with as little as 4 hours of daylight. As daunting as that sounds, more than 100 miles away, Russian crews are already building a link to the nearest railroad. These workers have built 55 miles of rail, and they've got 65 miles to go before they reach the river. Here's how they do it. A specialized crew works by hand to build the track in sections. Then this machine spits them out like a polar Pez dispenser. It can haul 100 tons of rail in temperatures 50 degrees below zero. Out here, it's so cold, crews can only work 4-hour shifts. More than 500 men have spent the last 4 years on the job, and they're going to be here another 5 before they're done. But the biggest obstacle they face isn't the cold, it's the permafrost.
Permafrost, by definition, is ground that has been frozen for 2 or more consecutive years. Over time, a vegetative mat establishes itself on the ground that's thick enough to insulate that and keep it frozen.
That frozen mat feels rock hard, but if the temperature were to rise above freezing, ice between the soil's particles would melt and the ground beneath the rail would sink. A disaster for trains. Just by clearing a path for the tracks, crews can inadvertently thaw the ground.
You're going to be building across virgin territory that is now treed or vegetated. You clear that pathway, you remove those trees, now you have solar radiation penetrating the ground directly, and it starts to thaw that ground.
Making this a construction nightmare. Permafrost covers more than half of Russia. If crews can't stabilize the rail here, the dream of building the Bering Tunnel will never get off the ground. The solution is to keep cool, and engineers use a buried thermosiphon, or heat pipe, to do it.
The pipe is filled with a gas under moderate pressure. The heat from the permafrost is absorbed into the gas at the bottom of the pipe. The gas rises, the heat is evaporated out of the cooling fin, and the gas turns to a liquid, drops to the bottom of the pipe, and absorbs more heat, and turns into a gas again, and you get the cycling effect due to gravity.
Bleeding off heat before it can thaw the permafrost helps the Russians stabilize this tricky ground. After they complete the rail line across the Lena, they plan to keep building north, all the way to the Bering Strait. If that happens, engineers will be one giant step closer to making the Bering Strait Tunnel a reality. But engineers first need to finalize their tunnel design to provide protection from disasters. If they expect anyone to risk their cargo or their lives for the 60-mile ride below the Bering Sea. A tunnel under the Bering Strait would re-establish an ancient continental link severed during the last ice age. Then passengers would be able to travel over land from London to Moscow to Washington, D.C. But those continents have different sized railroad tracks. North America uses the world standard gauge, 4 feet, 8.5 inches wide. But Russia's rails are almost half a foot wider. Fortunately, engineers have already solved the problem.
There's a retrofit system that you can put on a broader train system. Essentially, it's a second set of wheels, if you will, 6 inches narrower than the Russian set, and you can adapt them to those rail cars so you can accommodate either side.
As crews construct the tunnel, they could live in what are now 2 Arctic villages on each shore. Wales on the Alaskan side, and Yulin in Russia. These rural outposts would become sprawling boomtowns.
The staging and the economics, the logistics of undertaking something like this are probably unique on the globe of today.
But builders won't have to tunnel across that 60-mile gap in one go, because a lucky accident of geography may have cut them a break.
In the middle of the strait, we have the Diomede Islands. Little Diomede Island is American, Big Diomede Island is Russian.
If you aligned your tunnel to incorporate those islands, then you could actually break the tunnel into 3 legs.
Each segment would be less than the length of Europe's channel. But where to start digging?
It makes sense to tunnel from both ends, but overall, you would save time by tunneling from multi-directions.
Ideally, crews could dig on 4 sides, from both continents towards the islands, and from the islands back towards the mainlands. So the first step would be to bore between the 2 islands and connect the 1.5-mile gap. That would provide a large enough staging area for crews to simultaneously tunnel from 4 vantage points. But it's not a matter of digging a single tube from shore to shore. Crews would actually need to build 3 tunnels. 2 for train traffic in each direction, and a 3rd, smaller service tunnel between them. After the whole project is complete, this tube will carry fiber optics, electric cables, and energy pipelines. But there's a hitch when it comes to natural gas. The combination of toxic gas and a commercial rail line could be deadly. To be safe, builders would need to lay a gas pipeline at least 200 feet away from the tunnels.
Or you don't need to bury that pipeline. As a matter of fact, if you had problems with it, you'd want ready access to it.
Once the service tunnel is safely in place, crews could dig 1 traffic tube at a time. It would take 5 years working 24/7 to dig the first tunnel from coast to coast. The second passenger tube would take another 4 years. Then for the first time, people could cross the continents underground. That is, of course, if everything runs according to plan. Once engineers have cracked the historic challenge of constructing the longest tunnel on Earth, in the Arctic, below a frozen sea, they'll find themselves up against an altogether different kind of problem. How to ensure that their tunnel won't go down in history as the world's greatest fire trap. Sadly, there are ample lessons to be learned from catastrophes which have befallen other tunneling pioneers.
Now, at least 4 people are known to have died in a massive fire which swept through an Austrian tunnel.
About 50 cars were trapped in the tunnel. Only a few were able to turn around for safety.
In March, 40 people were killed in a fire in the Mont Blanc tunnel.
Experts now recognize that its ventilation system would be inadequate for a major fire where the death toll seems certain to rise.
Tunnels under the Alps have suffered some of the worst blazes ever. In recent years, nearly 200 people have perished in a slew of alpine tunnel fires. So emergency response crews in Switzerland are exploring new ways to combat this fiery plague. In fact, some of their techniques are so innovative that firefighters from around the globe come here to train. The Hagerbach Test Gallery, outside Zurich. Today, they're hosting a team from the Netherlands. They're here because there's no other facility in the world where firefighters can confront the burning beast inside the confined space of a real tunnel. This is the go-to place for Arctic engineers if they want to ensure that the Bering Tunnel would be safe. The Swiss lab is in a maze of tubes, thousands of feet beneath the Rocky Alps. Crews here have spent nearly 4 decades playing a fiery chess match with disaster, figuring out how to battle and prevent tunnel fires. Those long years of effort have led to crucial insights, lessons the designers of the Bering Strait tunnel will need to take to heart. Most critical to understand, fighting a tunnel blaze is more dangerous than battling a surface fire. In a tunnel, air circulation patterns favor the fire, not the firefighter. A tunnel fire can consume oxygen so rapidly that victims often suffocate long before they succumb to flames. Equally terrifying, the tunnel acts like an oven. The earth surrounding the tube forms a perfect insulator, exponentially raising the interior temperature. A typical house fire burns at 1200 degrees Fahrenheit, but some tunnel fires have cooked at upwards of 1500 degrees, hot enough to melt granite. But the worst part of a tunnel fire is the terrifying fact that there's nowhere to run. Even with so many lives potentially at stake, getting people out of danger can't be the firefighters' first concern.
The firemen learn here the highest priority: protect the building, cool down the building, then go inside, and then fight the fire, rescue people.
In a fire under the Bering Sea, the same techniques would apply.
In tunnel firefighting, rapid, targeted cooling will make rescue possible. Each square meter has to be controlled. We need to bring down the temperature so that firefighting forces can move safely.
The only way to fight the battle is to deploy the team in small squads, dispatching one group to the front for only a few minutes, and then continually rotating new fighters in when conditions become unbearable. In that way, they maintain constant pressure on the blaze. If the concrete isn't cooled down quickly enough, the hot rock can become so unstable that the tunnel can collapse, crushing or suffocating anyone inside. Yet as horrifying as tunnel fires are, heat and flames aren't the deadliest threats.
The most dangerous part in a tunnel fire is not the fire itself, but the smoky gas, which diffuses very fast. So survival becomes impossible for the people in the tunnel.
The ensuing fire triggered a series.
In the 1999 Mont Blanc fire, poisonous fumes caused most of the nearly 40 fatalities.
Seen by the thick black smoke in the tunnel still billowing from ventilation shafts this afternoon.
The victims died choking on noxious smoke, trapped inside a toxic 7-mile furnace. The Bering Tunnel would be nearly 10 times that long. With 64 miles of tunnel, one ventilation fan on each end couldn't move air fast enough. Even with the latest super-efficient fan designs, the tunnel would require multiple air shafts to the surface, spaced all along its length. But building impervious air shafts, snorkel-like, through hundreds of feet of water and ice would be next to impossible. Here again, the islands may save the day.
Diamide islands could be used for ventilation stations to supply air to the tunnel to the safe zones along the tunnel. The Diamide islands could also be escape zones or escape locations where people actually could get back to the surface from the tunnels if needed.
Experts believe that with more efficient fans and 6 air shafts, the Bering Strait Tunnel would be sufficiently ventilated for travelers to have a shot of surviving even the worst tunnel fire. With state-of-the-art technology and safety measures in place, the Bering Strait engineers will have done everything possible to prepare for an emergency. But some disasters just can't be prevented. After more than 12 years of construction, the Bering Strait Tunnel would finally be complete. For the first time in history, humans would forge connections between 5 continents: Africa, Europe, and Asia, all linked to North and South America by rail. Russia could transport enough natural gas to power all of North America. And China would ship goods from Shanghai to Chicago 4 times faster than by ship, slashing costs. But funneling so many riches through that narrow tunnel may be tempting fate. More than 12,000 years ago, the land bridge that used to link North America and Asia eroded away. Today, the tunnel could be destroyed again in an instant by an earthquake.
We're in a seismically active zone, and it actually crosses 2 tectonic plates. And that zone is very high risk of damage to an earthquake, which could certainly end up in flooding of the tunnel.
The state of Alaska experiences twice as many earthquakes as the rest of the United States combined.
A truck driver on the highway near Mentasta when the earthquake hit yesterday. His semi ended up inside of a break along the highway caused by yesterday's 7.9 magnitude quake.
But it rattled cities from Anchorage to Seattle down to Louisiana.
In the 20th century, Alaska experienced 3 of the largest recorded earthquakes in the world.
The toll of the dead and presumed dead went up today.
Quakes in 1957, 64, and 1965 rocked the region.
They figure Alaska may take as long as 5 years to rebuild.
Seismologists know the Bering Strait is dangerous, but it's what they don't know that is most threatening.
We know that there are faults out in the Seward Peninsula Bering Strait area, but we're not sure if we've identified all of them. In fact, we're quite sure we haven't.
So far, scientists have identified several active fault lines near the strait.
The map of earthquakes in Alaska does show us that we do have some intense hazards along the southern boundaries where the 2 tectonic plates meet. The Tintina Fault and Caltag Fault running east-west, the Kobuk Fault to the north of there.
Seismologists at the Alaska Earthquake Information Center in Fairbanks maintain a constant vigil, monitoring all of Alaska for quake activity. They searched for seismic hits in the Bering Strait using a monitoring station in Ten City, next to where the U.S. side of the tunnel would begin.
Yesterday we had a swarm of earthquakes in western Alaska. You can see there are 6 lines there, so basically it's 6 different recordings of the ground shaking in that particular location. This is where the first arrival came in. This is where the larger secondary arrival came in. So this series of earthquakes was big enough to produce measurable ground shaking in Tin City.
None of these tremors would have been strong enough to threaten a tunnel, but the zone is very active. So engineers would build their tunnel to roll with the punches, the best hope of surviving a quake's shearing force. It's an engineering problem that Alaskans have solved before, though on a smaller scale. Finished in 1977, the Alaskan pipeline lays a tube in a horseshoe-shaped cradle to adjust to any shake.
The actual transport tunnel would be on a shoe system that would allow lateral movement within a broader tunnel. If there's a seismic event, the tunnel can move laterally on those shoes, so it can flex with the seismic event and then readjust.
But there would be a limit to tunnel flexibility. If a 7.0 quake struck in the middle of the strait, the damage could be catastrophic. Builders would have lined the Bering Strait tunnel with emergency exits located every 500 feet. Massive doors could block breach sections, and sealed panic chambers could keep victims safe for up to 3 days, long enough for divers and rescue crews stationed on shore to come to their aid. Fortunately, the likelihood of such an accident is extremely low, and though it may sound far-fetched today, the technology to build the longest and the safest underwater tunnel in the world is within our reach. And on the American side, it just may be the perfect project for the country's most pioneering state.
In the course of history, Alaska has always liked the big project. It's just the nature of the country that we live in. Small things become big very, very quickly. The Trans-Alaska Pipeline, 800 miles of 48-inch pipeline, was a large project. The tunnel is really kind of symbolic of that. Mega projects for Alaska are not unique. We think about them all the time. The question is, where do we build them and at what cost and when?
You can pretty much engineer anything if you have the will to do it and if you have the money to do it. It is not technologically limited at all. We have the technology to build such a tunnel.
The Bering Strait Tunnel would cross the international date line, so travelers could leave Moscow and arrive in Alaska yesterday. With its completion, we could transform world energy and revolutionize global trade. In the process, we build an engineering marvel, a tunnel to tomorrow.